Okay. Two announcements first. The network issues has been resolved, so we have a network connectivity back. So you should be able to do the naps. But even the gateway, even if it has an internet, but it doesn't really have a DSN cache there. So maybe you launch your browser on your gateway and type a URL there, it may not work. But it does have internet. So the assignment is due on 2 weeks from now, the Sunday night, midnight. And we're going to have an in-class quiz this Friday, just 10 minutes. And the quiz will include everything we covered from the beginning of the class till now. So basically just network basics and security concepts. So everything we're talking about today will not be in this quiz. Yeah?
That's this Sunday.
What?
That's this coming Sunday, not 2 weeks from Sunday.
Really? Yeah.
It's almost September already.
Okay, I will change that later. Okay, I will email you guys later. Yeah, I think I made a mistake here. Okay.
It's not a big deal.
Yes, okay. Yeah, I made a mistake there. Cool. So last Friday, we talked about some security concepts. We talked about some security objectives we are trying to meet. So today we are going to talk about the crypto foundations that help us to achieve those security objectives. So what is cryptography? So cryptography means secret writing in Greek. And basically, it is a discipline that studies encryption principle and methods. And the scholars who work on cryptography, we call them cryptographer. So on the other side of the coin, we have cryptanalysis, which is a discipline that trying to crack the cryptography without using any known keys. So if you are the receiver of any encrypted message, you are the legit receiver of that message, and you are not going to use cryptanalysis. You are going to use a key to decrypt that message. But cryptanalysis studies how we can extract the plain text without knowing the key. So the scholars working on this is called a cryptanalysis analyst. So if we combine cryptography and cryptanalysis, we have this new umbrella term called cryptology. So why we are using cryptography? Because cryptography can ensure confidentiality, which means we can encrypt the message, prevent it from being reading by eavesdroppers, and we can ensure integrity, make sure that the recipient, when the recipient receives the message was not tampered or altered. And we can also use cryptography to ensure authenticity. That means the recipient can verify the identity of the source of the message. And also long repudiation, which means the recipient can be convinced that the said message is actually accurate. It is what actually happened. So what is the relationship between cryptography and security? Obviously, we talked about this several times. Cryptography is like the foundation for security. It offers the mechanisms to achieve those security objectives. But however, cryptography is actually a branch of mathematics. So all the great cryptographers, they are mathematicians. But security is different. Security is about math. It's also about hardware, about software, and most importantly, about people. Because people is actually the target we are trying to protect. And people is also the weakest link in security. So attackers, they always try to find the weakest link in a system. And in most cases, cryptography, the mathematics, is not really the weakest link. So we talked about the heartbleed attack before. So there was a bug in the OpenSSL library, which is an open source implementation of TLS and SSL. However, there is a bug, and by using that bug, remote attackers, they can do a buffer overread. They can read the arbitrary memory from the victim's computer, which means they can read the victim's private keys. However, you see in this example, the algorithm itself is not really broken. The key was compromised. However, the reason for the key to compromise is because it's a software problem. It's not really a crypto problem. So before we dive into crypto, there are several terminologies we should go over first. First, plain text is the message that to be transmitted or stored. And the ciphertext is the encrypted or disguised message. Key is the sequence that actually controls operations and behaviors of any cryptographic algorithm. And the key space is the total number of possible values of keys for a particular algorithm. So obviously, if the key space is bigger, it will be harder for an attacker to do a brute force attack to guess the key. So encryption is the process of disguise the message so it cannot be read by the attacker. And this process can also include both encoding and enciphering. And the protocol is an algorithm defined by a sequence of steps specifying the action of multiple parties in order to achieve a security objective. Obviously, we talk about the network protocols in this class, but there are also crypto protocols. The purpose of crypto protocols is just to build some secure communication channel or authenticate someone. So to achieve some kind of a security objective, not do some just to transport message. So crypto system is a combination of everything: algorithm, key management, or everything that is used to perform those crypto operations. So we talked about attack models before. In order for an attacker to attack a crypto algorithm, so there are many different models. First, we have a ciphertext only model, which means the attacker only has access to ciphertext. Obviously, attacker doesn't have the access to the keys. If the attacker is trying to compromise a key, it's not a part of cryptanalysis. We discussed that. So attacker has only access to the ciphertext. He doesn't know the corresponding plain text. This is called a ciphertext only model. And we also have a low-end plain text model, which the secret, which is a plain text, is known by the attacker, and the attacker also knows the corresponding ciphertext. So the attacker has many pairs of this ciphertext and plain text pair. And we also have a chosen plain text model in which the attacker do not only have access to plain text and also ciphertext. The attacker can also choose arbitrary plain text to encrypt it and get the ciphertext. So we see that those three models, the ability of the attackers get stronger and stronger. So there is a principle called Kerckhoff principle. It was published in 1883. So basically, what the principle states is a crypto system should be secure even if everything about the system except the key is public knowledge. So this principle is the principle all the cryptographers are following right now. So all the algorithms we are talking about, we are using in the real world, they are all public algorithms. So they are open to everyone. So everyone can try to attack it, try to compromise it. However, the goal is as long as the key is safe, even if the algorithm is known, it's fine. The attackers cannot really get any advantage of that. So why this principle is important? Because in reality, it's really difficult to protect the algorithm. The algorithm will be implemented in hardware, in software, and the attackers can reverse engineer it. They can, if you implement in hardware, they can capture your machine and try to figure out how the machine works. This is actually what happened like centuries ago. They have this Cipher machine, and if the Cipher machine is captured, and they will be able to figure out how it works, then the whole security system collapses. And it's very expensive if one algorithm is broken and you have to replace all of it. So right now, all our security, the crypto algorithms, the security of it, based on the key, not the algorithm. So the first type of crypto algorithm we are going to study is called the Symmetric Key Cryptosystem. It is also called a shared key system, or sometimes they call it a secret key system. So basically, this is how it works. First, the sender will produce some plain text message, and the sender will generate a key, or somehow it shared this key with the receiver beforehand. So then the sender input this plain text and the key into one encryption algorithm. Here the algorithm is symmetric, which generates the ciphertext. And the ciphertext, because it's encrypted, it can be sent over to the receiver through any channel, any insecure communication channel. So the confidentiality of this message is not protected by the channel, but protected by the crypto algorithm here. So after the receiver receives this ciphertext, it will use the same key and use the decryption algorithm to decrypt this to get the plain text. So the very important thing here is both the sender and the receiver, they are using the same key here. So sometimes in some algorithms, they are not exactly the same key, but it's very easy to compute the decryption key from the encryption key. So basically, we say they are the same key. And sometimes even the encryption algorithm is the same as the decryption algorithm. So a very interesting thing here is how can you actually exchange the key? Because key is the secret, is the shared secret here. So you can do that either through a secure channel, which is another channel different from this insecure channel, or you can distribute it beforehand. Or there are some protocols like DH protocol we will talk about maybe this week. Those protocols will help senders and receivers to negotiate this secret key. So if we represent this in math, we can say ciphertext is assigned to the encryption with the key as input and the plain text as input. And the plain text is just a description using the key and the ciphertext. So this symmetric, any symmetric crypto system has to meet those properties, so we can say the algorithm itself is safe. First, it should follow the Kerckhoff principle. So the security only depends on the key. So the algorithm should be public. Everyone should be able to analyze, try to attack this algorithm. And without this key, it should be very hard to decrypt the message. And also, computing the encryption algorithm and the decryption algorithm should be very efficient. So this can be done in a very timely manner. Actually, all the crypto system until 1970s, they were like symmetric crypto systems. There were no asymmetric crypto system until 1970s. So the asymmetric crypto system will allow the encryption and decryption use different keys. And we're going to talk about that next week. So in order to study how this symmetric system works, we are going to use 3 examples: Caesar cipher, Vigenère cipher, and Transposition cipher. And the first 2 examples, they are substitution ciphers. And we are going to show how it works, how they work, and why they are not secure. But surprisingly, if we combine this substitution cipher with transposition cipher, we can have some very secure algorithms. And all the algorithms we are using now, like AES, they're like a combination of substitution cipher and transposition cipher. So first, let's look at the Caesar cipher. So it was said that Caesar used this to encrypt messages to his generals. So what he did was he would take each letter of the alphabet and replace it with a letter of a certain distance away from that letter. So when he got to the end, he would wrap back around to the beginning. So for example, if that distance is 3, he said the distance is 3, then A will be replaced by D, B will be replaced by E, and Z will be replaced by C. So this is like a fixed table with this shift of 3. So in this case, if we say the number is 3 and we can get this table, this is a direct fixed mapping there. So if we have a table like this, and the plain text is attack, then obviously we can get the ciphertext DWWDFN. So what is the key here? So in symmetric algorithm, we have key, we have plain text, we have ciphertext. So this is a plain text, this is a ciphertext. So what is the key here? Yes, so the key here is the number 3, is the amount we shift a letter. Then how big is the key space? 26. Any other answers? 26 is almost correct. Actually 25. Because if you actually shift to 26, it will be the same, right? So only 25. So how can we attack this Caesar cipher? It's not very difficult, actually. So we are using a very strict model here. We're using ciphertext only model. So we assume the attacker only knows ciphertext. And obviously, the attacker doesn't know the key and also the shift table. So what the attacker can do is just make a list of all possible keys. There are just 25 of them anyway. And it tries to decrypt it with each key. Then he will get a 25 corresponding plain text. And he will just read all those plain text, try to say if there is any string that is recognizable, it's really English. If it is, then he successfully decrypts that. So why this cipher, this Caesar cipher, is really easy to attack? Is it because it has a very small key space? So the next one we're going to show is, even if we have a bigger key space, this kind of a cipher, this kind of a Caesar cipher is still subject to attack because there are some inherent weaknesses in this algorithm. To do so, we extend the Caesar cipher to a simple substitution cipher. So Caesar cipher is like a subset of a simple substitution cipher. So in Caesar cipher, we can only shift the letters. But in this simple substitution cipher, we can substitute any letter with another letter in this alphabet. For example, if A can be replaced by J, B can be replaced by L. So the distance between A and J and the distance between B and L, they are actually different. So this is not Caesar cipher. However, we're going to show they are still subject to attacks. So in this substitute cipher, how many keys are available there? How to calculate that? Arbitrary? Any other answers? Yes, so actually it's a factorial of 26. Because for example, for A, there are, should be 25. In this one, we can substitute one letter with its own. So we have 26 ways to substitute A, and we have 25 for B and 24 for C. So we have the factorial of 26, which is a huge number. So previously, when we attack Caesar cipher, we were trying to do a brute force attack. However, for this substitution cipher, if we still do a brute force attack, it will take a very, very long time. Actually, if every person on this planet, we try one per second, it would take 5 billion years to try all those keys. So obviously, this is not a feasible way. But we're going to show that still, this algorithm is not secure. So we are still going to use the Ciphertext only model. We use a very strict model for the attackers to show this is really easy to attack. So this is the Ciphertext here. What we can learn from this? We can learn there are VXY. So when we say this, the first thing you think is in English, some letters will show more frequently than other letters. For example, letter E will show most frequently, then letter T, then letter A. So then we count this ciphertext. We count which letter shows most. And we got a letter Y here. Then we replace letter Y with letter E. Then we got this message. We do this again for letter T, then we got this message. And this is called the frequency analysis. Obviously, the frequency in the ciphertext will not exactly match the frequency in plain English. But in most cases, there is a strong correlation. And the longer ciphertext you have, the frequency of the letters in the ciphertext will be the same as the frequency in plain English. So besides the frequency of letters, we can also use the frequency of words. For example, here we have a TKE. So what is the most likely term at the beginning of a sentence? Maybe the. Yes. So actually, what we can also find that the TKE is the, and we can replace K with H. So there sometimes we also need to guess a little bit, but with this guessing, with this pattern analysis and the frequency analysis, eventually we will be able to decrypt this message. So this is a message actually I copied from Wiki about the Sun Devils. So this is the substitution cipher table I used. And you can try this using this link. So you can see that even though this algorithm is much more secure to the Caesar cipher because we believe the key space is much, much larger. However, the algorithm itself is still very easy to attack. It will not take 5 billion years for us to crack this. It will only take maybe 10 minutes for us to manually crack it with the help of computer, maybe 30 seconds. So what is the inherent weakness in this kind of algorithm? Why it's so easy to attack? So we learned that a large space of keys is not enough to build a secure algorithm. So basically, we say that the Caesar cipher and the substitution cipher, they all belong to this category of cipher, which is called monoalphabetic, which means the same plaintext letters are always replaced by the same ciphertext letters. So as long as that table is fixed, that substitution table is fixed, A is always replaced by a letter, a fixed letter. So this kind of a substitution cannot hide the statistical properties of plaintext. If E is the most popular letter in English, then switching it to Y will make Y the most frequent letter in your ciphertext. And it also doesn't hide the relationship in plaintext. So the E will always be replaced by the same fixed character. So if we have two E's together, it will not be mapped to two different letters. It will always be the same. So actually, it's also because English itself is very redundant. Because of redundancy, we have a different frequency for different letters. So how can we make it harder for the attackers to crack? So we are going to try to hide the statistical properties. For example, if we have a E in the plaintext, in the ciphertext, we try to generate different letters for this plaintext E, maybe 12 different symbols. And this is called the polyalphabetic cipher. Actually, it's just like we use the substitution cipher many times at a different stage. So one character, one letter will be replaced to different letters. And another way to enhance this is called the transposition cipher. And the transposition cipher will change the order of letters. So previously we were saying the order of letters, they have not been changed. So we are going to talk about the polyalphabetic cipher first. So in 1550, around that time, Vigenère invented this cipher. Now we call it a Vigenère cipher. So this cipher is like a very difficult to crack. It was considered unbreakable for 300 years. And in 1860s, and by Charles Babbage, yeah. So in 1940s, two of them actually they independently discovered the way to crack this password. So basically, this Vigenère cipher tries to mask the frequency. So to do that, they make one letter in the ciphertext corresponds to multiple letters in the plaintext. So the frequency analysis, the pattern analysis we discussed before, would not work on this cipher. So any message encrypted by this algorithm is actually like a collection of many shifted ciphers or substituted ciphers. And the keys previously we are using is just one number in Caesar cipher. We are using number 3, number 5. But here we are using multiple keys, multiple numbers. So we're going to show it. So here, this is a plain text. So each plain text letter will end with the key. And the key is just not one letter, it's multiple letters. And if we use all the keys letters, the keys repeat from the beginning. So we add them together, then we do a modular 26. So frequency analysis doesn't work here anymore, but we're going to show how we can break this. So the primary weakness of this cipher is the key will repeat itself because the key is not as long as the plain text. So the key, since the key will repeat itself, we can take advantage of the fact that if there are some repeated word, that is maybe the plain text for the repeated words, the plain text part, they are the same, and for the key parts, they are also the same. So the same plain text with the same key, they will generate the same ciphertext. So the method to attack it is called Kasisky Test. So the purpose of the Kasisky Test is to find the length of these keys, which is the first step to crack this Vigenère cipher. After we find out the length of the keys, we can just divide those messages into many segments. And each segment, we can treat them as a simple substitution encryption. Then we can solve them one by one. So here is an example. We are using the key king here. So king, we can map it to different numbers. K map to a number, I map to a number. So we have the key, we have the plain text. So we plain text and the key, we got the ciphertext. So when we try to attack it, we try to find the repeated words in the ciphertext. For example, here we find the BUK twice. There were 2 BUK words. And if we look at here, we can say we have this BUK because the key is the same. They are all ing. And the plain text part, they are also the same. So people discovered that there is a relationship between the distance of those 2 strings, the repeated 2 strings. So the distance here is 1, 2, 3, 4, 8. So 8 letters. Actually, they discovered that the key, the length of the key can divide the global common dividers of all the distance. So previously, here we are just showing 2 repeated words. But actually, if we have a very long ciphertext, we can find a lot of segments like this. Then we calculate the distance. Then the rule here we know is the length of the key must divide the great common divider of all those distance of repeated words. So using this test, we can easily find the key length of this Vigenère cipher. And also from there, we can just break it down to cracking substitute cipher, which will be much easier. So the next cipher type we're going to discuss is called a transposition cipher. So transposition cipher is different from the substitution cipher, 2 substitution cipher we just looked at. A transposition cipher is a cipher in which the plaintext message is rearranged by some means agreed upon the sender and the receiver. So rearrange means we are changing the order of the letters. So we are in this transposition cipher, we are not changing the letters. We are not replacing A with C. We are just changing the position of it. So this is also called a permutation cipher. Here is one example. So the plaintext we are using is today is Monday. I'm using a plus to replace white space, which will be more clear for us. So we write it this way. Every row we just write 5 characters. Then we read it in a counterclockwise style from top left. So here, then the ciphertext will be T plus O N D A Y. So we do this. So we have the plaintext, then we have a ciphertext. So you can see that we're not even substituting any letter here. We're just changing the order. So obviously, we have to share how we are going to encode this with a receiver. So it turns out this transposition cipher is also subject to attack. First of all, when we reorder the letters, we are not changing the frequency. So still, we can use the frequency analysis. And if we do a frequency analysis, we find the frequency of words in this ciphertext actually match or is close to the frequency of English. We can see that it is using a transposition cipher. It is not using something else. By attacking it, we need to sliding pieces of the ciphertext around, then look for sections that look like English words. For example, here we have in the ciphertext we have day. We have day here, and this is actually part of Monday. So we can get some clues there, and it's not really difficult to attack this transposition cipher, but it's a little bit harder to explain that. So I will just skip that part. So the interesting part is we showed 2 different basic symmetric key encryption algorithms. One is substitution, one is transposition. And we showed that both of them can be easily cracked. However, the strange thing is if we combine them together, if we have 2 substitutions, we have a stronger substitution. If we combine 2 transpositions, we will have a stronger transposition. But if we combine substitution with transposition, we make a very hard to crack cipher. So this is actually proved in theory by Shannon in 1945. So this new type of cipher is called a product cipher. It will combine 2 or more transformations. And later, next class, we will see that the AES, they are going to use a substitution, then a permutation, then they will do it multiple rounds, like more than 10 rounds to make it harder. So this is really interesting. By combining 2 things very simple, we got a new cipher which is very hard to crack. And there are some principles, but we will discuss that next class. So the next class, we're going to talk about the modern symmetric algorithms, which is a combination of substitution and the permutation. And we're going to talk about different modes of using those algorithms. And we are going to also cover hash and map. Yep.
The assignment is due this Sunday or?
No, next Sunday. next Sunday. Not this Sunday. Yeah. Yes.
When we log into the environment,
Uh-huh.
the TA has already signed us up.
Yes.
And you know how we have to change our password right when we log in?
Yes.
I was having trouble changing my password.
Uh-huh.
Is it okay if I keep the password given to me?
It's not safe for you to do that.
Oh, really?
Yes.
Okay.
Because someone else can access your account because your email is public, right?
Right. I was trying to change it, and it says, use 2 letters, 2 numbers, and
It's too complicated, so you don't want to.
I followed it, and it still wasn't allowing me.
Really?
Yeah, I over and over I tried 15 different passwords, and it wasn't changing it. So I don't.
Maybe there is something wrong, but it's not safe for you to keep the default password.
I'll try again, but it wasn't working. So
Okay.
if I have trouble again, I should show you in person.
Cool. Hey,
Rashid, I think you made a bunch
Sure.
of late registers.
do you have a pen I can borrow? So where should I sign it?
I think you.
Here, right?
I think so. It's the instruction.
Okay.
Can you write on the back of the page the work I missed or something? Because they need your. This is mine.
Okay.
I want to write like the work I missed or changes or something like that.
Okay. So
You have to write.
So if there is any sick issues, you need to show a proof of that for like a hospital notice or whatever. So normally what you do is when you submit this, they will email me, right? Ask me to you are missing anything.
You want. So
Okay, so I just put it here. Okay.
Yeah.
So this is your last name or first name?
This is my the first name.
That's your first name?
Yeah.
So what is your last name?
This one. McBady.
Okay. Mu
MAQBA.
B-A-L-I?
Yeah.
Oh, this is a Q here?
Yeah.
Okay. B-A-L-I.
So
Okay.
let's write the work I missed or something like that.
Homework and assignment deadlines. Okay. I'll type my name here. I hope this is enough.
Yeah, thank you. I appreciate it. Yeah.
This is yours.
Good.
So Friday I'm gonna be out of town. I'm gonna be in Colorado. Is there any possible way that I could like take the quiz like beforehand or
Is there a reason for you to?
just
Family issues? Let me think. Normally, family issues, it's not allowed,
Okay,
Mm-hmm.
that's fine.
Okay. A midterm, maybe I can do